I don't know how much you guys know about the topic of interpolation, so I wonder to see. Go ahead.
So in task 1, we have do some basic things on task 1. So this parameter setting. So
what's a lean space? 0, 1. Okay, good, very good.
yeah,
And then
we use the sign 2 n pi x for the function we want to simulate.
Good.
So we run the interpolation. So we have tried different sampling point, which is the big M. So
yeah. So does this make sense to you? Did you do the interpolation before? Did you see polynomial interpolation? So did you study it before?
No. So I just studied the PDF when I finished this task.
Did you? I mean, because you know the Taylor expansion, right? So you've done the Taylor expansion for sure, but you haven't done any polynomial interpolation yet. Have you done the Fourier series?
Yes.
You studied the Fourier series?
Yeah, I studied from the signal and system.
Okay, very good.
Yeah. So
go ahead.
But I didn't know this type of interpolation before, so I just run the function that from the Python.
Does it make sense to you? Does it? Yeah. Does it make sense to you as a mathematical operation?
Maybe it makes sense.
Okay, because just look at this, right? So it's clear that this is a discussion for everybody, right? So it's clear that if you look at the Fourier transform, right, you can see that there's a way of approximating a function. So somebody gives you a bunch of points, and you want to have a compact way of representing the function. So you look for the function which is band limited that fits the set of points that you have. Is that okay? Then another thing that you can do is to use, for example, a polynomial. So you describe the function as a polynomial that passes through the points. But the barycentric approximation is a rational function. So does it make sense to you that? Yeah, we'll see. We'll discuss in a second. But you understand that it's like there is a type of functions that you choose, and then you try to summarize the function, summarize the points that you're given through the interpolation. Okay, go ahead. Let's see the next part of the code.
Okay, so I've run the model.
Let's see the figure. Oh, no, go to the figure.
Okay, so I use three layers. So each layer have 64 neuron. Okay.
Wait.
So
go up. Well, go to the figure.
Go up. Okay.
This figure here. Tell me what happens in this figure.
So I've tried different big M. So if the I guess if the sample point become too close, so the weight that calculate here will be very large, since the xi minus xj will be very small. So it turns out that the weight will be very high. So it will have some impulse response in this point. So it's not just the impulse thing. So it's not stable when the big M become very high.
Very good, very good. It makes sense, right? Because you are sort of pinning the function. You're pinning the function in more and more points. But this is a rational function, right? So a rational function, when you are close to, you understand the roots and poles of the function, roots of the function, poles of the function. You understand?
A little bit, yeah.
Yeah. So when you have a 0 in the numerator, then the function spikes up to infinity.
Yeah.
Because it's a rational function. So that's a game that you are playing here. Okay. Very good. Go ahead.
So the observation right now is I try the number of sampling points. So here's the M equals to 10. So it looks like this. So the green line is the prediction of the neural network. Yeah. So
just a second. Stay there a second. Don't rush. So can you stay on the figure? Stay on the figure. Good. So you have the true function. The barycentric interpolation uses only the red points, or also uses other points? Only the red points, right?
I use the sample point for training the DNA.
Good.
Yeah.
Good.
So that's the result. And
okay.
I just have this figure. So M
Yeah,
is
good.
25. So 51.
And then you see, very good, very good.
Yeah.
Then you see that there it becomes unstable. Very
Yeah,
good.
and 256. So yeah. So so that's what our group are done right now. Yeah.
Good. Okay, good.
Mm.
So you understand the stability. Let me take some notes, right? So you understand the stability issues of the interpolation. When you train the DNN, okay, so you train the DNN. Just remember that when you do the DNN training, you have to, there is something to understand there, right? Because of course the data set will be very small, so you have to augment the data set with some other points. Okay, you understand it? And then tell me about the groups. Everybody's in the group, everybody's talking, everybody's participating. Everything okay?
I think some of the teammates haven't done anything yet, but there's some teammates. I discussed with some of the teammates, but some of the teammates, the other teammates are disappeared. Yeah.
Hopefully
So
they will emerge soon.
Yeah. So I try my best to let everyone can do something in the future.
Okay. And you're communicating over line, over Slack. How are you communicating?
We haven't made an online meeting yet, but just talk in the chat, online chat.
Okay. Okay. Good. Yeah. Okay. Very nice. So group 1 is there. Let's hear it from group 2.
Okay. Thank you.
Thank you. Train DNN, group 2. FFT. Group 2? Is that where is group 2? Come, guys. Oh. Guys, what's happening with group 2?
Hi, I'm a member of Group 2, and as far as I know, it looks like that we haven't started doing this challenge yet. So.
Okay, but did you guys talk to each other? Did you guys communicate?
I'm actually not quite sure because I just got back from the US like 2 days ago.
How was the competition there? How was the ICML stuff?
Hello, teacher. May I ask some question? I'm Group 2 student.
Okay, go ahead.
So is Challenge 1 doing this week or next
No,
week?
it's not, every 2 weeks. Every 2 weeks.
So it's next week, right?
So next week is the deadline. So 1 week we do the mid challenge.
Yes. We have created a chat room, and we are trying to distribute our works right now.
Good. But are you the leader, or are you just one of the students? Is the leader for group 2?
We haven't decided who's the leader yet.
Okay.
Right, and that's how we done right now.
Okay, so basically, just to repeat, so the first week, right, you ask questions, you come, we discuss, because the challenge is very open, right? So the first week we discuss to see what's happening, and then the second week you have the deadline, okay?
Okay.
Good. Okay, anything else from group 2? Anything that you want to discuss? Yeah.
Not yet, because we're still thinking who's writing the coding parts and who's writing the math parts, probably.
Okay. Yeah, just because basically the first week is if you have any questions, that's what the time where you ask, right? Because then if you make some conceptual mistake the second week, then you cannot ask me. So easy, right? So the first week is to make sure that you are on the right direction, right? So it's for your benefit. It's not that.
Oh, okay.
Yeah. So next time, try to do at least by the first week, at least make sure that you understand the job that you have to do. So if you have any questions or any doubt, you can ask me, right? For example, you see that the issue with this interpolation is that if you have too many points, then the interpolation spikes up to infinity. Also the interval, right? You have to decide which interval to use, because the longer the interval, the higher is the chance that you get a pole in the interval. So yeah. So next time, try to ask some questions.
Oh, okay.
Okay. No problem. Group 3, any questions from group 3? Anything from group 3?
Okay. 4 of our members have joined the Slack group, and we are researching the theoretical things about mathematics. So after this, we will start coding.
Okay. Yeah. Any questions about the interpolation? Is it clear to you why we need the interpolation? The discussion about false and zero.
All right, fine. No question. Thanks.
Okay. Good. Yeah. Anything else from group 3? Okay. Anybody else from group 3 that wants to discuss something? No.
We are still distributing our work. We just get all members yesterday.
Okay, very good. Yeah, so it was a little bit my fault that we didn't post until Saturday, but yeah. Anyway, so for, as I said, for the other groups, I try to come with some questions so that next time you're prepared. Okay, very good. Let's see group 4. Any questions from group 4?
We have gathered all our members, and we originally planned to discuss about the challenge tonight. So basically, we haven't done anything yet. So sorry about that.
I mean, it's as I said, it's the first challenge, but basically, yeah. So the idea is that in between, like every 2 weeks, there is a challenge, and the week in between, the first week of the challenge, you can ask me questions, right? So again, it's for your benefit. Very good. Let's see. Huawei, I think, I don't know if it's Huawei, it's here. Huawei, do you want to present something? Otherwise, we go to the class material.
Oh yeah, I can present after class. Yeah.
So you want me to go first and then you present?
Yeah, that's what we agreed upon, right?
Well, however you prefer, right? If you want to go first, it's fine.
Oh no, I insist. Please, you go first.
Okay. I go first. So I posted the slides for this week here. So let's go through the slides first, and then so I will present a little bit about the barycentric interpolation. Okay.
Okay.
So just for you guys to understand, right? Because how we finished last week is that we say that DNNs are universal interpolators, right? So you can use a DNN to represent any functions, right? And so this week I want you guys to see this, right? That if somebody gives you a certain set of pairs, X and Y pairs, then what you can do is that it is useful, right, to find a function that interpolates between these points, so that let's say you can predict what is the value of the functions on the points that you have not sampled. Okay, and I want you to guys see the difference between the interpolation that you obtain with a DNN and the interpolation that you obtain with other methods, such as the barycentric interpolators. And I want you to see that you can train a deep neural network to do the interpolation as the barycentric interpolation. Okay? Good. So you should be seeing my. I shared the wrong. Let me share another window. Let me share the PDF window so I can go full screen. So if you want, we can. If you want, we can go to the slide of the presentation. Let me just ask a second. Let me just ask in chat. Do you want to go through the text of the challenge together today? Question mark 01. Please answer in chat. Okay, so as we stopped last time, we said that the DNNs are universal interpolators. And we got to this slide, right? We said that we have a single neuron. This single neuron is performing this sort of sigmoid activation. And then what we want to do is we want to learn the weights such that the prediction is close to the labels. And the idea is that the network will produce a prediction, and then there is going to be a true label. And for example, the prediction will tell us what is the probability that the label is equal to 0. And then we can check with the true label. And then we are going to teach the network to correctly label the samples in the dataset. And we're going to do so by changing the weights of the single neuron. So the idea is that we have to define a loss function. And the loss function will be a measure of fitness of the prediction of the network and the true label. Right? So we are in supervised learning. So when we have a set of inputs, we know what will be the correct output, and we can choose a function to measure how close are the prediction to the network to the true label. So the idea is that we will have this function L, right? L for loss. This is the usual way of indicating the L. And this function measures the goodness of fit of the prediction of the network and the true label. And crucially, we see this function as being a function of the weights of the network. So we are saying if the network has weights from omega 0 to omega 4, then we want to optimize this function over these weights so that then, we can teach the network to produce the output that we desire. Very good. We're going the wrong way. Sorry, guys. I have to remember this way. So the idea is that we have this loss function, and we imagine that this loss function has a minimum, and the minimum is this omega star. So omega star describes the best set of weights for the network to produce a prediction which is consistent with the true labels as measured by the loss function. So what we want to do is that we want to find the derivative of the loss function with respect to the weights, and we want the derivative to be equal to 0. Right? So this is the usual convex optimization setting, right? So generally, this loss function as a function of the weights is going to be a very complex function, which is not going to be convex, which is not going to be easy to optimize. So we want to say, as we said last time, we want to use stochastic gradient descent to find the minimum numerically. And the idea is as follows, okay? So we start from a certain set of weights, which are our omega 0. And what we can do is that we can measure the performance of the network when the weights are omega 0. So what we do is that the loss function will measure the closeness of the prediction of the network to the true labels. We're going to average this prediction across all the entries of the data set. And then we're going to get this first value, L. Then what we want to do is that we want to take the derivative of this loss function at omega 0, and we want to take a step in the descending direction of the gradient. So we want to take a step in the direction of steepening descent of the gradient, and we want to obtain a new set of weights, which we're going to call this omega 1. These are the first set of weights that we produce in SGD. And again, we evaluate the loss function by averaging the loss over the dataset entries. Then we're going to measure the gradient, and then we're going to take a step and repeat until we're going to get hopefully to our minimum. Of course, in general, we're not guaranteed that we're going to obtain the optimal set of weights. So we might need to start from multiple initialization point. We might need to repeat SGD with a different set of entries in the data set, and so on and so forth. But basically, this is the basic idea of stochastic gradient descent. So the idea is that we understand very well how to do this when we have a single parameter, because in a single parameter, the descent direction of the gradient is just another function. And in your life, maybe you have never thought about higher dimensional derivatives. But basically, if you have a function that has key entries, right, you see that this is a function L that has a number P of independent variables. You need to have a definition of gradient that is a high dimensional gradient. Or you can ask yourself, what do I expect the gradient of a function with P independent variables to look like? And the answer will be something like this. Okay, so if you want to define what is the derivative of a function of P independent variables, you will do this. You will say that the gradient is a vector. Okay, so this is a vector. This is a vector of function. So each entry in the gradient vector, it's a function. And in each entry, we have the partial derivative of the function with respect to one of the independent variables. Okay? Good. So remember this, right? So this is a function of p independent variables. It means that I have these p objects. When I put inside the p objects, I get one single scalar out. Okay. Then I want to define a derivative of this object. I want to define a gradient of this object. So I want to ask myself, what is the direction, right? In which direction, as a function of the independent variable, is my function increasing or decreasing? And so it's clear that since we are in a p-dimensional space, this direction should be a p-dimensional vector. Okay? And so how do I calculate the vectors? Of course, I need a definition that tells me each single coordinate how it is obtained. And each coordinate is obtained as the partial derivative of the loss function with respect to the weight. Okay? So remember that this is partial derivative, right? So what you do is that this is a function of p independent variables. You imagine that in this case, all the independent variables between 2 and p are fixed. And so you see this function as being a function only of the variable omega1. And you take the derivative with respect to this. Okay? So this is, yeah. I forgot about group 5. Sorry, guys. Very fun. So let's do this. We go a little bit. And then we go back to group 5. Sorry, guys. Yeah, very good. Okay, so we also go through the presentation together. Okay, good. So is this? Please call me just Stefano. Don't call me Dr. Stefano. Okay, or Professor Stefano is the worst. So tell me if this is clear. Here's the concept of p-dimensional gradient clear. 0/1. Because it's sometimes it's I think it's the first time that you guys see this concept, right? I just want to make sure that you understand it clearly. Please answer in chat while I close my door so I don't disturb everybody. Guys, answer in chat. Is the concept clear? Good. Of course, the smart people are the ones that answer first, right? So it's clear. But remember, okay? So we have a p-dimensional variable. We want to define a gradient. So this has to be a vector. Even if the function is from p variables to 1 variables, when I look at the gradient, this is a p-dimensional vector, okay? So the gradient is not a scalar, it's a vector. Good. Very nice. So now we are in this pickle, right? In which we are trying to take a gradient descent, and the gradient descent is going to be a gradient. And the idea is that we want to do this, right? So usually we represent it in a single variable because it's easy, but basically this is the point. And now we want to discuss the following, right? So if we take a step, how should we choose the size of the step so that the following doesn't happen? When I'm far away from the function, I get closer and closer to the point. But then when I get closer to my minimum, I take a step which is too large. And so I keep oscillating back and forth. I keep oscillating back and forth in my estimation. Okay? So you can imagine that you're at this point, you jump here, you jump here, you jump here, then you jump back, right? And then you start oscillating back and forth, and you never get to the minimum. Okay? So you can ask yourself, once I have the direction of the descent, how big is the step of my descent so that I don't overshoot my minimum? Okay? So the idea is that we have the old weights, we want to get to some new weights, and we want to take something which is a step in the direction of the descending direction of the gradient. And the idea is as following, okay? This derivative of the function with respect to the independent variables is going to be a p vector. These old weights are a p vector. And we have to choose how much to move. And usually people love to move according to a variable nu, which is very small. And this is usually called the learning rate. Okay. So the idea is that we want to take as small of a step as we can manage without without having too many steps in our stochastic gradient descent. So the choice of the learning rate, it's a very tricky choice. It's something that can be optimized, and people in the literature, they spend a lot of time trying to describe what is the best choice of the learning rate. And yeah, and so given that, let's say you have a good choice of the learning rate that comes from your experience, then you will get an iterative method, which we call gradient descent, which is you start from initialization, and then you iteratively do the following. You take your current weights, you evaluate the derivative of the function according to the current weights, you get a derivative, and then you update the old weights with the current gradient to obtain the new weights, and this is what we call gradient descent. And notice that here we use usually this notation to indicate the iteration step. So here in the parentheses, I have the iteration step. So at omega of parenthesis 0, I have some random initialization. So I start my algorithm from some random points, and then I keep iterating over this. Good. So everything is nice so far. We understand the algorithm pretty well, but we have the issue that we need to calculate the derivatives, okay? So this is something that might have a large complexity or a small complexity. We still don't know, right? You can imagine that, for example, take some of the functions that you know, right? So take, for example, a trigonometric function. If you take a trigonometric function and you calculate the derivative, the complexity in a sense remains the same because you go from cosine to sine, right? So in a sense, the complexity of calculating derivative is the same as calculating the function itself. But then you can imagine that if you, for example, if you have a polynomial and you calculate the derivative, the complexity of calculating the derivative is lower than the complexity of calculating the function, because the derivative is a polynomial of one less degree. And so there is this relationship between the complexity of calculating the function and calculating the derivative. It's not obvious. It's not something that we can always rely on. And now we have decided that we're going to work with deep neural networks. And we know that calculating the output of a deep neural network is something relatively easy, because we have each different layers. For each layer, we calculate the weights, the activation, and then we can do it quickly. So the error, the question that remains is how difficult it is to calculate the derivative of the weights, of the loss with respect to the weights in a deep neural network. Is this something very crazy, or is it something that we can manage computationally? And you know the answer, because since deep neural networks are trained so efficiently, you know that the answer is going to be yes. Okay. Sorry, guys. The controls here. The controls here are a little bit crazy. So, what are we going to use to simplify the calculation? So we know that a deep neural network operates in layers, and we know that the output of a layer will be the input of the next layer. And intuitively, we want to try to use this in order to simplify the calculation of the gradient. Okay, so let's go to some of the rules of derivative for high-dimensional functions. So these rules here, right, they will look familiar to you, because these are for single dimension here on the left. This is for a scalar variable with one independent variable, and this is a vector function of p variables. So let's see that what we hope happens, meaning that we have some rules of derivative that holds for low-dimensional functions, so one input, one output, and we want this to hold also for vector functions, so functions where the number of independent variables is p. Okay, so if we have y is equal to g of x, everything is a scalar, and then we have a z function, which is an f of the y, so that the z is an f of g of x, and you ask yourself, what is the derivative of z with respect to x? You have your beautiful chain rule, which is partial z, partial y, partial x. Okay, so this is understood to you guys. So if you go into the algebra with the definition of gradient that we had for a function of p-independent variables, you will see that the same happens. Let's say that we have a vector y equal to g of vector x, and we have a z. So now z is a scalar here, right? Z is a scalar. This is an f of y, f of vector y, which is an f of g of vector x. You can ask yourself, what is the derivative of my scalar z, okay, with respect to the entry I of the vector x? Okay, so this is the ith entry of the vector that describes the derivative of the scalar z with respect to the vector x. Okay? Scalar, vector. The derivative is a vector. I'm telling you what is the derivative with respect to the coordinate I of the vector x. Okay? Then the chain rule also works, right? Meaning that we do go from the partial z, partial y, j. Then I go partial y, j, partial xi. And I sum over the j. So you can imagine this way, right? So I do the partial of my scalar output with respect to all of the coordinates of the vector y. And then I multiply by the partial of the coordinate y, the coordinate j of the vector y, and the coordinate I of the vector x. Okay? So z is a scalar, y is a vector, x is a vector. You go from z to j in y, and then from j to x, and then you sum over everything. You sum over the possible j. So j is sort of the intermediate position. You start from the scalar x, you arrive to the scalar xi, and then you sum over all the partial. Good. So this is helpful, right? Because we know that in a sense we want z to be the loss, y to be one layer of the neural network, x to be the next layer of the neural network. And then since this rule applies, can be applied iteratively, right? If we have a longer chains, let's say that we have a q of an f of a g of an x, right? Then the chain rule will still hold, right? So we will concatenate all, let's say, the intermediate independent variable between z and xi, and we will obtain the ith entry of the derivative of the scalar z with respect to the xi, okay, to the ith entry of the vector x. Good. Okay, so usually you guys don't see this type of rules in your linear algebra, but it's not too difficult. Okay, so now we are at this point. Now we want to apply, we want to show that if we apply these chain rules to the calculation of the loss with respect to the weights, then something nice happens and things simplify nicely. Okay, so let's do the example with logistic regression, right? So the idea is that we have a total loss. The total loss is the sum of the loss over all the elements in the data set. In this case, we take the logistic regression loss. So this is what we have. We have the summation of the I in the data set, and we have the true label yi for that and for the data set, and we have the prediction of the network, which is the pi, and the loss is yi log of pi plus 1 minus yi log of 1 minus pi. Remember the interpretation that we had. Pi is the confidence that the output of the network is a 0. So if your label, if the true label is 0, and your function and your network is very sure that the output should be 0, then you have a small loss. If the function, if the network wants the output to be a 1 and your true label is 0, then you have a large loss. Very intuitive. Then remember that here we are in a single neuron case. So this pi is a sigmoid, right, of 1 over 1 plus e to the minus omega t times x. X is your vector of features that enter in the network, and omega is the weights. So clearly we want to take the derivative of the loss function with respect to the weights. Okay, so the derivative is additive, right? So the sum of the derivative is the derivative of the sum, or maybe the derivative of the sum is the sum of the derivatives. So what you do is that you take the sum, the derivative of the loss with respect to the weights is the sum of the derivative of each of the entries in the data set with respect to the weights, and then we sum. And here you see that we have these two components of the loss. Let's call it Li of A and Li of B. No problem. We go through this. We can break it again in the sum of the derivatives because derivative is linear, okay? So it's a linear operator. Then we have these strange objects, right? We want to take the derivative with respect to the weights of this function. Again, remember that this is a scalar function with a vector input. We want to see the loss of the sample I in the data set. Let's say A is the first part of the loss, right? So with respect to the weights, And we have this strange vector function, which is the yi is a scalar, and then we have a log of 1 plus 1 plus e to the omega t, so this is a vector, times x. So here, it's something that you don't have much intuition for, because usually you study the derivative of function of one independent variables a lot, so you know all the derivative rules. So if somebody gives you a vector function, you're a little bit confused, like, what are the derivative rules for these vectors? But it turns out that the derivative rules for the vector functions are sufficiently similar to the derivative rules for the scalar function. So in this case, for example, we have a linear function. The psi of I is omega t times x. And if you take the derivative according to, again, the rules that we described before, we have this derivative is equal to minus x. And this is like saying that if this was minus omega times x, the derivative with respect to omega of this function will be minus x, which is what you would expect in the scalar case, right? So we go through these rules, right? So the second one is for the exponential. So derivative of omega t times x. If you did this in the scalar case, it's going to be just the exponent, right? So this is also what happens here. And then you go through the various composition of vector functions in order to go from linear function to exponent to ratio of an exponent to log of the ratio of an exponent. And for each of these steps, you know what are the partial derivatives until you get to the final result, which is a vector. Okay, and this vector describes the derivative of the loss function with respect to the weights. Let's go through this together a little bit. The first step, you have a linear function. More precisely, this will be an affine function. Okay. So the partial derivative of xi with respect to omega, as you said, is minus x, very reminiscent of the scalar case. Then you have exponent, right? So you have xi2 is equal to e to the xi1. So we are taking the concatenation of the function, and you know that the derivative of xi2 with respect to xi1 is e to the xi1. Okay, but xi1 is defined as minus omega t times x. So you know the derivative here is going to be e to the minus omega t times x. Okay, good. Then you take the 1 plus this. So the derivative, the partial derivative is only 1, right? Because if you take the derivative of 1 plus xi2, it's just 1. Then you have the xi3 and xi4, which is 1 over something. Derivative of the inverse is like in the scalar case, is 1 over 1 plus the independent variable square. Then you have the log. You know the derivative of the log is 1 over. And then what we do is that we compose all of these partial derivatives as follows. Derivative of L1 xi5, xi5 xi4, xi4 xi3, so on and so on and so forth, until you do the full chain, right? And then you do the full chain, you are taking the product of all these objects, right? All these objects like this, and when you compose them all together, you get this output. Okay, so this is to show you the composition rule for the derivative of this function as the product of partial derivatives. Very good. So once we do this object, we get the full derivative, and now we can move, guys. Just a second. Now we can move, we have the calculation of the derivative. Now we go back and we have to choose the learning rate. So when you first do this, you are kind of confused because you say, well, when I was younger, right, I will have a convex function. And in order to find the derivative equal to 0, I will just equate my gradient to 0. And I will find the solution x for which the gradient is equal to 0. And in a sense, I will know exactly where the minimum is. The point is that when you have a function which is non-convex, then you can have multiple local minimum. And so you cannot rely on the gradient being equal to 0. And generally, the expression is so complicated that finding the 0 of the function is not obvious. So you prefer to do this gradient descent, which is computationally more efficient. Then the next step that you ask yourself is like, what is this business with the learning rate? And the idea is that you want to take conservative jumps because you do not want to overshoot your solution. So in a sense, when you choose your learning rate, you're always in this in one of these three conditions, and you try to balance things so that you're always in the last one. Let's see what's happening. So in the first condition, I know I have to move in the descending direction of the gradient, but I do not know how far away is my starting point from the solution, from the optimal set of weights. So what I do is that I choose a learning rate which is too conservative, and so I never make progress. Okay, my learning rate is so small that I'm just making a tiny progress, and even after 1 million iterations, I'm far away from the minimum. So I'm wasting time, I'm wasting computational resources because I'm taking a lot of derivatives, and I'm far away from the zero. In the second case, I overshoot the learning rate. So what happens is that I start very close to the zero, and I just need to move a little bit to get there. But I choose a learning rate which is large, so I take very large steps. So what I do, I oscillate around the function, the minimum of the function, and I never get there. I keep getting stuck to some points, and I never get to the true zero. In the last case is the best case, where I choose the learning rate just right, so that I take a step which gets me straight to the minimum with the correct, let's say, with the correct number of iterations. Okay? So very tricky to decide where you are and to adjust the performance of SGD according to this. But basically, what you can do is that you can try to look at the following plots and try to understand what's happening. So what you will plot is that you will plot the value of the loss function as a function of iteration. Okay, so every paper, every presentation that we will see in this course will have a plot like this. And this is, of course, the test loss versus the number of iteration. So what happens is that if you go too slow is that your loss is not moving, or it's descending very, very slowly. And so you see that there is not much improvement as the number of iteration goes. The other case is where you have a very large variation of your loss function. So you jump up and down, but you don't seem to go down. And the best case is the case in which you start somewhere. You are sort of stranded for a certain amount of time, so your loss function does not change much. Then you get lucky and you take a step in the right direction, and then you see this sort of exponential decay of the loss function with iteration, and then you know that convergence happened, right? You know that you started from somewhere, you quickly travel to the minimum of the function, and then once you get to the minimum, you cannot go anywhere. Okay, good. So deciding what is the optimal learning rate, it's an art. It's something that people learn from experience. There are many algorithms to do so. There are scheduling. There are checkpoints. There are entire books that are written about this, right? So it's, of course, it's a very delicate topic, so we can discuss it later. And then there is the issue that since the function that we are dealing with when we look at DNNs are very highly nonlinear function, there is the issue to know whether we are in a local minimum or a global minimum. So the issue is that if we were lucky, right, the derivative of the loss with respect to the parameters of the network will be a nice convex function. So we know we don't need to worry, right? We start from wherever we start. We just take stochastic gradient descent and we end up in the global maximum and we are happy. In reality, what happens is the following, that if you take two different starting points and you run SGD, you will end up at two different values of your optimal weights omega, okay? So you repeat your initialization 10 different times, you let SGD run for 1,000 iterations, then you look at your weights, and you will see that the weights, they are very, very different. Okay, meaning that every time that you have an initialization, you end up in a different local minimum. And this is something that you experienced already, I think, partially. For example, if you take MNIST, MNIST is a very simple data set which is linearly separable. So wherever you start with the initialization in MNIST, you always end up at the same local minimum. But if you take CIFAR, right, if you take 10 different initialization, you will end up at 10 different values of the omegas of your final weights. And there is no way in which you can even say, oh, this set of weights is close to this other set of weights, right? Because these vectors are of dimension, let's say 3,000. And what is the probability that you start from two different initialization on a space of 3,000 independent variables and you end up on the same points after 1,000 iterations of SGD. Of course, it's very difficult. Okay. So how would you deal with this, right? Because if you start from a certain initialization, you do not know if you really ended up in a good local minima, let alone in the global minima. And so the only thing that you can do is to have multiple random restarts. But having multiple random restarts is, of course, very, very computationally complex, right? Because it means that you have to restart the learning process multiple times, and that takes energy, that takes time, that takes resources. Of course, the resources are computer resources, but we cannot discount the cost of running computers. And something that you can do is that you can perturb your loss function. So the evaluation of the loss function gets perturbed by noise, so that you can imagine that if you get stuck in a local minima here, then by adding noise, you are pushing your computation to go beyond the current minimum. Okay? Good. Okay. Let's switch presentation. Any questions so far? So we do 10 more minutes, then we switch to the next, okay? Sorry for group 5, guys. I forgot. Okay. Any questions so far? No? Okay, good. So let's go one more set of slide on SGD, and then we switch to the throwaway presentation, and then we go together to the description of the challenge. Okay. Okay, good. So let's continue on this topic. We saw how to calculate the derivatives. We discussed the learning rate and the global minima, and then what we want to discuss now is the influence of the data set. So this is also something that you're experimenting with in your current challenge. And part of the challenge is to experiment with the effect of the size of the data set. Okay? So what we want to do generally in one epoch is as follows. We take one element from the data set. We feed it to the neural network. Okay? So we pass it to the neural network. We see what is the output. For this output, we compute the gradient. As we saw before. Then we calculate the update rule for the weights. And then we repeat this set of operations from 1 to 4, let's say 10,000 times. And then we hope that by doing this, we are going to obtain a set of weights for the network, which performs well. So usually we use this terminology. We say that one epoch is a full forward pass and a full backward pass for all the training examples. So you take all your training set. So the forward pass is the inference pass, is when you put the inputs and you obtain the output. The backward pass is the calculation of the gradients, because the calculation of the gradients goes from the output of the network back to the input. And then we call this object, these two operations a full pass, right? We call this an epoch. Then we want to do this stochastically, right? So we want to stochastically choose the examples that we're going to put in this step, okay? So let's see what is mini batch stochastic gradient descent. So if we do one example at a time, this is sort of inefficient. So what we want to do is that we want to choose a mini batch. We want to say that we take a subset of the elements B, and we stochastically select this subset of elements, and then we say, well, if we calculated the gradients over the full data set versus if we calculated the gradients on this subset, then the results of these two operations will be close. So I save computational resources by choosing only a subset of the elements of the data set. And I know that even if I do this, my gradient descent is going to perform well because the gradients are going to be similar, right? So we call this mini batch SGD. right? So you choose a batch of data, right, like a subset of the data, and you run the loss function over a subset of the data. Now, why would I want to do this, right? Because for each element in the data set, I have a certain cost of evaluating the gradient, right? And this cost is fixed. So why would I like? Why would it change? What is the logic behind this? Of course, because I expect that if I use fewer elements in calculating my gradient, so I have a stochastic evaluation of the gradient, then the quality of the gradient will be degraded, so that then the progress of SGD will be affected, so that I'm not saving anything, right? Because I have a worse gradient. So if we have a worse gradient, I mean I have to do more steps. So eventually the complexity should remain the same. And the intuition is correct and incorrect, meaning that usually when you choose the stochastic gradient, usually when you choose the learning rate, you want to be conservative because you don't want to skip over a good solution. So usually you tend to be conservative. And so you have to run many iterations. And you know that at the beginning of training, your network is going to wander around regardless of what happens because you are far away from the optimal solution. So usually it is okay to use a small batch because there is an exploration aspect of SGD at the beginning of training. So you know that you're going to do many steps. And so you want to reduce the calculation of these many steps because you know that eventually you're going to have this sort of exponential behavior, right? When you get close to a solution, then SGD will zoom in on this solution. And once that happens, the gradient is going to be very sharp, very large. And so it's not very much affected by the evaluation. So usually people prefer to choose a smaller batch size and run the iteration for longer than choosing a larger batch size and run SGD for fewer iterations. Okay, good. So this is the plot that you have in mind. You have your whole data set. You have your whole training data. You chop up your training data in mini batches randomly. Then you present the mini batch to the network. You're going to obtain a forward pass. In the forward pass, you're going to obtain the losses. And then you're going to do a backward pass. So you're going to obtain the derivative of the losses, derivative of the loss with respect to the weights. And you're going to obtain the network. You're going to update the network, and you're going to repeat this step multiple times. Okay, you repeat this for all the possible mini batches. This is constituted an epoch, and then at the next step, you re-randomize the data and you rerun the process. Okay. So what happens in one epoch is that you take all your training data, you divide into mini batch. The mini batch are selected randomly, right? Are formed randomly. Then also you randomly select one on a mini batch. You feed the neural network, you calculate the gradient over the whole mini batch, then you update the weights and you repeat this, and this forms one epoch. Okay? So the idea is that if you had the full gradient calculation, you will have this function. If you do a calculation over the batch, then this calculation will be approximated, right? So you're not going to be able to see the same quality of gradients, and also the evaluation of the minimum will be affected by the batch. But the idea is that if you have a local minimum in the full gradient calculation, you're also going to have the same local minimum in the batch calculation. Of course, if the batch is reasonably chosen, right? If you choose a batch of dimension 3, of course, this might not be the case. But the idea is that, you know, you want to move along these directions, basically. Okay. So the way in which people refer to this objects sometimes changes through the literature. So sometimes they call it batch, mini batch, and usually when you choose the mini batch size, is always power of 2. And everything in machine learning is power of 2 because, of course, it's run over GPUs, and GPUs, they do good operation on multiple of 2s. So your mini batch size is always 256, 512, 1024. But because, of course, the GPU accelerates computation for the matrix multiplication, which is used for gradient calculation. And it does so well when they are power of 2. And the idea is that if you again look at your training performance and you try to guess whether your batch is too large or too small, you will see this, right? So if you have a very small batch size, if you have a batch size which is too small for your current learning problem, you will see a very jumpy performance of SGD, meaning that you will be, let's say, in this case, right, where the minimum does not correspond to the global minimum. And if the batch size is too large, then you will see that an epoch takes too long, right? So the calculation will be too slow. So you always try to push the batch size to be as small as possible before you see some negative learning performance. Okay, good. I was not sharing the slides. Which, no, you cannot see the slides, guys? Yeah, I was sharing this, right? Good. You guys cannot see?
It's all gray.
Ah, because I have to share. Let's try again. I have to share before I go in presentation mode. Mystery. Okay. Guys, what's happening?
Okay.
I just Adobe, right? Like I did before. Oops. Adobe. Adobe, what are you doing to me?
Nope. It's still gray. It's still the same.
Mystery. Okay, it doesn't matter. Let's switch to the web page. We figure out the issue. Maybe there is some issue with the sharing. Okay, let me just repeat briefly what we did based on the slides online. Let me just pull up the slides online. Yeah, so gosh. This is a Chrome tab, right? Can I show the Chrome tab? Can you see this, guys? No, right?
No.
What's
happening? It's still gray. Gray everywhere.
Okay, let's see this. This should work.
Oh yeah.
No, I cannot share it. It's something with the Chrome tab. Yeah, let's try the Chrome tab. Okay, let me repeat this very quickly. So okay. Let's repeat this. So we are saying this. This is the epoch that we are discussing. This is the derivative. This is the loss with respect to one sample, which is the loss with respect to the mini batch. Then this is what happens when you feed multiple mini batches to the network. So you see that you take the training set, you divide in mini batches, and you go on. Then this is the pseudocode of one epoch. So randomly form the mini batches, randomly select the mini batches, feed forward, calculate the gradient as average over the mini batch, use this to update the gradient, and then repeat the steps until you run out of mini batches. So you call this one epoch, right? So the size of the mini batches, say, determine this, and this is what you want, right? So this is when the size of the mini batch is reasonably close to representing the gradient, so they are similar. So when you do SGD, it's good. This is when the mini batch is too large, right? So you have you do small steps because your mini batch is large, and this is when the mini batch does not represent the true function. So the minimum of the gradient, the minimum of the function as evaluated over the mini batches is different from the minimum of the function as evaluated over the full gradient. And this is what we discuss, right? So this is batch size, mini batch size. Here, if the large batch size, of course, it's very computationally very heavy. So you try to break it down into small mini batches, and the quality of the mini batch will be revealed by how jumpy is the local mean. Okay, let me do the last set of slides. Then we switch task. So I just want to do backprop. I want to finish with backprop, so I know that I have to open it with I have to do it with I have to open it with Adobe, otherwise. Okay, so that was easy. If I go in presentation mode, also should work, right? Full screen mode. Okay, and I close the window here, and you guys don't see the window. Okay, backpropagation. So now you understand everything. Now let's go back to the evaluation of the gradients. So we saw that this is the evaluation of the loss function for the logistic regression, so classification problem. And this is the forward and backward pass, right? So in the forward pass, you see that you calculate these intermediate calculation steps. So this is the affine step. This is the sigmoid output. This is the loss function. Then when you do the backward step, you see that you use the results of the evaluation in the forward step to calculate the partial derivatives, right? So here you have the true label y and the p, right? So the p is evaluated at this step. So here you calculate the derivative between the p and the h, and here you have the input x, right? So here you have the beta values of the linear activation. So you have delta L, delta P, delta H, delta B. Okay, so the evaluation of the forward pass helps you the evaluation of the backward pass. So that's why you always need to do one forward pass and one backward pass. And yeah, so you have to repeat this for the two parameters that we have in this very simple network, which are the beta 0 and the beta 1. So the coefficients for the 0 degree coefficients and 1 degree input coefficients, and then you can extend this to multiple layers. So what you can do, and it's a good exercise, is to do it, let's say, for sine activation function. So you can write down and do the exercise for the sine, and then yeah, then you will see the influence between forward and backward propagation, and then of course. These calculations are modular, right, in the number of layers, so that if you have one layers, right, or two layers, the evaluations are sort of, they follow from one another, right? So they follow the same set of equation, so that the computation of the backward pass can be generalized to any number of layers. And we want to sort of reuse this in order to reduce the computational complexity. And yeah, so this is where we're going to go next. So we want to have a formalism to calculate the backpropagation with respect to the weights. And we wanted this method to be flexible and to produce an exact computation of the gradient, because we already have some noise in the gradient calculation, which is introduced by the fact that we use mini-batch. And of course, we want this to be as computationally efficient as possible. And the key is going to be our chain rule as before. So remember that we saw this chain rule, and this allowed us to calculate, let's say, a fairly complex derivative, right, through a set of simple steps. So this is the trick that we used. So you can think that what you're given to you are simpleton functions. So you have some very simple functions that you can express as with one line of code. And then what you do is that you cascade these simpleton functions to produce the full derivative. And notice that basically what you want to do is something like this. This is an identity function, so the input is equal to the output. And you want to also define for this simpleton function its derivative, which returns a constant. Then this is an affine function, and you want to derive the derivative of the affine function, and so on and so on and so forth. And basically, what you would like to do is this follow. When you go to the forward pass, you select this function. Then for each of these functions, you know the derivative. And when you do the backward pass, you select among these derivatives. And this is exactly what happens. So when you define a network, let's say in Python, you define the forward pass. In the forward pass, you use a simpleton function to construct each of the neurons. And then in the backward pass, what you do is that you create a computational graph. You reverse the connectivity of the network and calculate the backpropagation rules. And this is expressed through a graph, very easy. So let's see what the graph looks like. So we start simple. Let's say that we have an input, then we have an affine function, and then we have then these are the parameters omega. Okay, so then this goes into, let's say, the exponential. So this is e to the minus, right? Then we want to put the constant, the other one, and then invert everything, right? And then you see that you have all the different computations that get you to the final loss function. And then it's clear that each of these functions here, it's a simpleton, right? It's a very simple function for which we can compute the derivative. So we go from the omega to the x, and we want to sort of backpropagate. We want to move backward over this graph to go from the calculation of the loss back to the calculation of the derivative of the loss with respect to the weights. Okay. So this specification of the network structure can be done efficiently because you don't actually specify each neuron at a time, but you have layers, and layers are uniform across the network. So you know that you can easily generalize the construction of the graph with respect to each layer of the network. Then you build the computation graph, and then after you build the computation graph, you have the rules of the derivative for each of the singleton function to calculate the backward pass. So the idea is as follows, right? So this is, again, imagine this for one input, one output, single neuron network. Then this can be extended to any number of layers, any number of neurons. So you have the computational graph that brings you from the input to the loss. You have the derivative, and then you have the intermediate computation of the forward pass. Then you have the intermediate computation of the backward pass, and then you cascade everything so that when you're given a numerical loss of 0.003, right, you can compute the derivative with respect to the weights. Okay, very good. And so on the forward pass, you need to store the intermediate values of the forward pass. And then in the backward pass, you just do basically multiplication, right? And the rules of an application that you have to follow will be determined by the computational graph. Good. Yeah, so that's it. So this was an example of phase detection. So doesn't matter. Okay, very good. So I think it's all where you go next. And then let me see if there is any questions. Otherwise, any questions? Any question, guys? What is the presentation? Any questions? Any questions? Otherwise, to where you go next, and then once you do your presentation, I'll go through the challenge description, and then we move forward.
Okay. So let's recap on the concept of barycentric interpolation. So for a given set of data points, like so, these are the polynomials, and we have an evaluation point. Let's say we want to evaluate a point in x equals 2, just an example, to show what the missing data might look like. Now, here are the metrics and the definitions of the barycentric weights. And I think it'll be more interesting if we just go to the code part. Just the math formulas are an eyeful. It's just, too much to handle for now. So, as we have learned in Calculus 1 or Calculus 2, this is the Lagrange interpolation implemented in Python. Now, for today's topic, we'll learn about the barycentric weights. Now, the definitions is as such here. So, in this notebook, I want to present to you why barycentric weights is generally better at handling a large data set rather than using Lagrange interpolation. Now, in this challenge, we use a rather large data set. So, about the barycentric weights, whenever that the nodes are the same, we don't calculate the reciprocal. So this should be pretty much self-explanatory. And now for the interpolation part. First, we calculate the numerator. And where's the definition? I have it somewhere. Sorry, I'll just pull up it. Yeah, we can see from the challenge document that the interpolation mechanics is like this. Oh, this is the weight we talked about, and the numerator is as such. Yeah, okay, so let's do a little experiment, but using a small data set, because here are the 4 data points, and we need to guess the y value at x equals 2. So currently, we can see much different in the computation time. Okay, but what if we have a larger data set, say 100 points, and you can compare the Lagrange method and the barycentric method and the optimized module provided by the SciPy library. We can see here, this is, we're trying to interpolate the sine function. And we can see that Lagrange methods is not very stable at handling a larger data set. See, right here. And at both endpoints, Lagrange oscillates much more than the barycentric weight method. As to why the endpoints have such errors is some phenomenon called the Ranges phenomenon. And here's the proof in Chinese. Yeah. Okay. So to show exactly how the execution time differs, I have another experiment with different numbers of interpolation nodes right here. So 5, 10 through all the way through 500. And here you can say the standard Lagrange have O to the power to the n of power of 2 computational efficiency, whereas barycentric only has O of n. And I think that's pretty much it. Yeah, I'll wrap it up here.
Okay, very good. So let's go to group 5. Do you want to go next, please?
Okay. So far I found my group member, but
Okay.
there's another member I haven't found him. And currently I do some practice, and I finished a little bit test 1 and test 2, so I can
Okay.
show you my screen.
Go ahead, please.
Can you see?
It's starting. Yeah.
Okay, so currently I make a footnote in every sentence, and I think it's easy to understand this. And first we define the model of the neural network, this part.
Mhm.
And second, we use the active function, and we will change the active function in different part. And the next is the training setup.
Multi loss. Yeah.
Yeah, and after training the model, and we can predict the point. Okay, so the basic idea is we use the sample point. We choose 50 sample points, and we will have a generative function, which is regarded as a ground truth function. So we will discuss the ground truth and the train model, and discuss the loss function, and output will like this one.
Very good. Very good.
So it's basically the test one's content, and we will change some, for example, the size and the deeper, or occasionally the active function part here.
Correct.
If you choose another active function, for example, I use sigmoid.
Activation. You mean activation function, right? Activation.
Yeah,
function.
sorry, activation function. For example, sigmoid, and it will have a bad accuracy. Yeah, like this one.
Yeah. So because the sigmoid is bound between 0 and 1, right? So for example, the difference between the ReLU and the sigmoid, right, is that the sigmoid is bounded between 0 and 1. So the output is always going to be between 0 and 1, right? So you see here that the function goes between 1, 5, and something, and the sigmoid cannot output that. Yeah.
Yeah, and besides, in order to compare the accuracy, I let the function, I mean the original function here, become more complex, so that I can compare their accuracy. Yeah.
Mhm. Yep.
And I also use tanh.
TANH, okay.
This part, and it's pretty fit the true function here. So I think it's a good activation function. So yeah, and the later one is the another activation function. It's ELU.
Yeah.
Yeah. So another change is the deeper of the hidden layer.
Correct. Correct.
So this part, this part is the deepened hidden layer I add, and you can see that it's pretty fit the true function here, which this true function is the ground true function, because we use the interpolation method to let the function become a true function, right? So if we let the hidden layer become deeper, and it expected to have a more low loss function, right? So, but that doesn't happen if we just add too much hidden layer. You can see in this part, the train model is deviate from the ground truth, so it's pretty weird. Yeah.
Oh. Very nice, right? You see that always having deeper function is not always better, right?
Yeah, it's not always goes better, so it's pretty weird.
Makes sense. Yeah. But next week you will tell us more about this. Yeah, but very good. Right?
Okay. So another change is about data size and the size of the hidden layer.
Yes.
I also make some practice here. And okay, so it's about the test one. And test two, I guess, is to generate some functions. So I actually have some method to generate function. So first, I use the random frequency and random amplitude, so that I can generate a family of sine and cosine function. So it's pretty convenient to have us generate 100 function. For example, this part is 479 and 643 and so on. And if I to run again, it will pick another function here. Oh, sorry. You can see it's quite different here. Oh, sorry, maybe I should remove this one.
You should change the seed.
Yeah, I should change it. So it's different, right?
Yep.
I forget, sorry. So I think I just think why it's not changed. Yeah.
The seed is not gonna change.
Yeah. It's embarrassed. Yeah, so it's different. And we can do different functions here, and then we can compare the accuracy. So it basically the same coding with the test one. And but we have some coding to generate the family of function, which we use the random amplitude and frequency. So the outcome will like this one. Yeah. So basically, it's so far I have finished. So
Yeah.
maybe
The coding part is not the difficult part. I think it's more the intuition, right? Trying to gain some intuition on this is gonna be the interesting part, right?
Yeah, I maybe I will improve a lot in about this coding and to find the reason why the deeper hidden layer will not have a better loss function. Yeah.
Okay, very good.
Yeah.
Good. Okay, so focus on the interpretation by next week. Okay, because with these things it's easy to do numerical experiments, but then try to collect some intuition, try to learn something from these numerical experiments. It's sometimes it's not easy, right? Because there are so many things that happens at once that it's hard to, let's say, gain some intuition of what is happening.
Yeah.
Okay, let's go through the challenge together a little bit, and then I'll let you guys go. Okay, so first of all, I would like to discuss this, right? So if you see the FFT transform, the barycentric interpolation, the polynomial interpolation, the Lagrange interpolation, these are all functions in which you are given a certain set of samples, and then you want to generate a function which interpolates between these points. And you want this function to have some nice property, right? For example, to be smooth. And sometimes it's hard to convey to you guys why you want to do this. And the idea is that you can have many points, but you don't want to store these points because you know that you can express this pattern with a few parameters of a certain function. Okay, so imagine that you have a function of 1,000,000 parameters, but you don't want to keep in memory these 1,000,000 parameters, and you are happy to do the following trade-off. Instead of storing the parameters, instead of storing the points, you store the parameters of the function. Then calculating the function will be harder than finding the points in memory, but you're happy to do so because you have this trade-off between complexity and memory. Okay, so imagine this: you want to store the cosine, for example. Okay, so you don't have a nice algorithm to calculate the cosine. So what you do is that you take a supercomputer and you calculate the cosine very precisely for all the numbers between 0 and 2 pi, and you just store them all in memory. So when somebody writes cosine of pi over e, you will go in your memory and you will go scan down your memory and find what is the closest point in your memory where you have the evaluation of the cosine for this value, and then that's the output. But of course, in the current technology, searching in memory, it's much more expensive in terms of time than evaluating a function. Okay, so you will be happier to have maybe a polynomial of degree 10, whatever, that interpolates the polynomial values. And once somebody asks you for that cosine, you go and evaluate the interpolation function at that point. Okay, so that's why this is a fundamental engineering problem, right? Because you want to reduce memory access, you want to reduce memory storage, and so you're always happy, generally, to store an interpolation function instead of the set of points. Okay, and you can imagine, right, that in that the deep neural network just does that, right? So you can imagine that the example that we go before, right? You go to the doctor, you measure some your weight, your height, your age, and then the doctor tells you what is the likelihood that you're going to get a heart attack in the next 6 months. Of course, what we could do is that we could have a data set, and when you go in, they compare your data to the data in the data set, and they see what is the closest case to you, and they tell you this is the probability based on all these other cases that we have in the data set. But generally, we prefer to have a neural network that has learned the parameters of the network from all this data, and it gives you a very quick inference because you are just evaluating this, let's say, 3,000 parameters of the network instead of going through the records of 1 million people, right? So the problem it's in this sense, right? That these interpolation functions, they provide a lot of power in this sense. And the idea that I want you to understand is that when you interpolate between these points, different interpolation techniques have different properties, and the deep neural network can learn these different properties of the interpolation if you do it correctly, right? So you can learn to be smooth, you can learn to be continuous, you can learn to have a finite derivative, and it all depends on how you generate things. Okay, good. So why do we choose the barycentric interpolation? Just because it's cute, right? So because usually you don't see this. The idea is that you'll have a rational function, and the evaluation of the weights is very simple. And since this is a rational function, it doesn't have the issue that polynomials have, because polynomials, they tend to go to plus infinity or minus infinity, but the rational functions don't. So usually they are easier to deal with because they don't tend to shoot up to infinity. But of course, what happens is that if this evaluation here at the bottom is very close to 0, then you're going to have a very large spike. So this is what I want you guys to see, right? So the interpolation is just different from what you've seen before, but it has advantages and disadvantages. So the idea is that you are given a set of points and you will calculate the barycentric interpolation, right? And basically from these points, you choose a certain smooth function, a rational function to interpolate between these points, and then you see what is the evaluation, right? And this is the example. No problem, right? So this is the code for the barycentric interpolation, and you do the example of the sign. Very good. This is the example of the sign. Then this is where you have to sort of this is where you have to play around a little bit. So the idea is that you randomly sample the points, then you do the interpolation, right? And then you try to understand what is the function that you interpolate as the number of points changes. And this is something that you guys already saw. And you saw how if you increase the number of points, then the function loses the smoothness, okay? Good. Then the idea is as following. So group 5 was doing these cosine functions, but actually the objective is to use the rational functions and have a neural network learn these rational functions. So the idea is that you generate some random points, you construct the barycentric interpolation, and then you treat this barycentric interpolation as the function that the network has to learn. Okay? So the idea is that you generate a bunch of samples, right? For each of the samples are evaluated over a barycentric function, and then you choose the parameters of the network, and you see how it goes. Okay. So this here you do it with a single function. So here you choose the point, let's say m point x and y. You find the barycentric interpolation. Then from the barycentric function that you obtain, you get a set of data samples, and then you teach a single network to interpolate a single function. So you train the network to produce the barycentric interpolation. Okay, so this is task 1. Task 2 is the following. Instead of considering one single barycentric function, now the input of the network are the various points fixed over a certain set of support, and then you want the network to learn how the barycentric interpolation would have interpolated that point given its neighbors in the support. So here you're doing upscaling. Let's say you're given n points of the evaluation of a barycentric function that you generated randomly, and you want to predict the other m points which are not in the support. Okay, so notice that these two networks are different, right? So here you have the input is one scalar x and one scalar y, And the network is just learning the one input, one output function, okay? So this is one function, but here is different. Here you have a subset of input indices, okay? Okay. And then for these input indexes, the network, you want to produce an interpolation across the entire function, okay? So let's say that you have n input points and you have m output points. You want the network to learn that if you take these points in input, then the barycentric interpolation will produce this upscaling of the function, okay? So in task one, again, task one, you have a one input, one output neural network. In task two, you have an n input, n output neural network, okay? Is this clear? Good, then, yeah, it is clear. Is this clear? Task one is one input, one output network. Task two, n inputs, n outputs. Okay. And then, of course, we play around with the total number of neurons, with the depth, and so on and so on. And also the size of the data set, and the type of activation function. Okay? Guys, again, please be careful, okay? So task one and task two, they have different sizes of the network, okay? Any questions, guys? Okay, good. So I'll be here for other 10 minutes if you have any questions. Otherwise, we update next week. Please, yeah, be careful because it's a tricky, yeah. There are some tricky things about the challenge, okay? Okay, good. I'm going to be here 10 minutes if you have any questions. I'll mute myself. I'll see you next week otherwise, okay? Ciao, guys.
Guys, remember to fill out the student info. Some students haven't filled them out. I'll send the link here.
Yeah. Also, yeah, there is this startup competition. One of my students want to participate. So if you want to participate to the startup competition, let me know. I'll put you in contact with my students.